In this video, we're going to talk about 3.1 Objective 3, where we solve applications involving average and instantaneous rate of change in derivatives. So let's go ahead and get started. One of the main applications that we have for derivatives is to talk about instantaneous rate of change, such as instantaneous rate of change of position is going to be velocity in our first equation here. So S of t is our position formula, negative 16t squared plus 76t, and our a equals 2, meaning we're approaching 2 seconds here. So s prime of 2 is going to be limit as t approaches 2, negative 16t squared plus 76t, and then negative 64 plus 152, 4, that's 8, it's 88, divided by t minus 2, and 76 is 2 times 38 is 2 times 19, so there's only a common factor of 4. So s prime of 2 is equal to limit as t approaches 2 of a negative 4 times 4t squared minus 4 goes into here 19 times minus plus 22 over t minus 2. So s prime of 2 is equal to limit as t goes to 2, negative 4 times, and there needs to be a t minus 2 over here to cancel with this t minus 2, which means this has to be a 4t minus 11. Negative 11 minus 8 is negative 19. So this is negative 4 times 2 minus 11. Negative 4 times 8 minus 11 is negative 4 times a negative 3 is a positive 12. And we are in seconds there, and let's see, we're in seconds and in feet. So we're in feet per second since we're in velocity. There we go. Right, just check that. 12 feet per second. Perfect. All right. Clear. We've got flow rate here. So the volume at time t is 3t. Find v prime of 16. So v of 16 is 3 times 16 is 48. Limit as t goes to 16, 3t minus 48 over t minus 16. Since it's a linear equation, we know that the flow rate has to match the slope of 3. And so this is an instantaneous rate of change, and we are in, let's see, gallons per minute. And this happens 16 minutes after the faucet is turned on. This is what t equals 16 would mean. All right. That one was pretty straightforward. Now we have d of t is equal to 16t squared. We want to find d prime of 16 So d of 16 is 16 times 16 times 16. That is 2 to the fourth. 2 to the fourth times 2 to the fourth is 2 to the 12th. So that is 4 times, I know 2 to the 10th is 1024. So 1024 times 4 is 1696, 4096. So D16 is 4096, but it's going to be important that that is 16 times 256. It's going to be what I need to think about because this has a 16 out here, as that'll be a common factor. So limit as t goes to 16 of 16t squared minus 4096 over t minus 16 will be limit as t goes to 16 of 16 times t squared minus 256 over t minus 16 is limit as t goes to 16 of 16 times t plus 16 times t minus 16. 256 is a perfect square of 16 times 16. There's our t minus 16 that cancels top and bottom. So our limit is going to be 16 times 16 plus 16 is 256 plus another 256, or 512. So we have 12 to instantaneous speed. There we go. 512, 512 feet per second, 16 seconds after being dropped. So that is C. Yep. All right. Now let's look at number 4. Derivative of the function is given at point. Here we have this force function that is proportional to the square of the distance. This is gravitational force. Pay attention to here. The x is in meters here, and force is in newtons. So when we have our rate of change, we're going to have newtons per meter for our derivative. F prime of x will be in newtons per meter. So let's find f prime of 13. It's going to be limit as x goes to 13 of k over x squared minus k over 13 squared is 169 over x minus 13. Let's multiply by 169 over 169 and by x squared over x squared to make a common denominator. It's equal to limit as x goes to 13 of 169k minus k x squared over 169x squared, then times 1 over x minus 13. So I want to factor out a negative k from the top. Make that x squared minus 169 over 169x squared times x minus 13. We limit as x goes to 13 of a negative k times x plus 13 times x minus 13 over 169 x squared, x minus 13. X minus 13s will cancel. That gives me negative k, 13 plus 13 over 169 times 13 times 13 is another 169. So this is going to be negative 26k over 169 times 169. And this is 2, and this is 13, and 2 doesn't go into 169 at all. So this is going to be 169 times 13, 27. 18 and 2 is 20. That's 5. That's 169 when we slide over. That is a negative 2k over 2197. Negative 2k over 2197. And this is an instantaneous rate of change of f prime of 13, and this is going to be newtons per meter. And this is going to be 13 meters for our distance. Let's look at number 5. So v of t is given to us as t minus 18 squared. It's a stopping distance. T can be anywhere between 0 and 18. Notice that v prime of t is going to be the same thing as acceleration. So that's going to be measured in seconds for time. V is measured in meters per second, so we'll be in meters per second, or another way to say that is meters per second squared. We'll be using this notation here, but in physics you'll see seconds squared when we have something per second, and then per second again we'll write seconds to the second power for our unit. All right, so v prime of 7. So I need to find v of 7 is a negative 11 squared is positive 121. So v prime of 7 is limit as t goes to 7 of t minus 18 squared minus 121. I'm actually going to use a factoring technique there that may seem unusual to you, but I'm going to do it anyways. T minus 7. So this is going to be limit as t goes to 7 of this is t minus 18 plus 11. And this is t minus 18 minus 11. A plus b, a minus b. And then that's t minus 7. So this is limit as t goes to 7 of t minus 7. And then t minus 29. I think that's just easier factoring for me than trying to think of 29 times 7. So there we go. That's going to be 7 minus 29 is a negative 22. And these are in meters per second per second. So that's that unit. And then v prime of 7 represents the instantaneous rate of change in the car's speed at t equals 7 seconds. So that is C. Right. Let's look at our last problem here, number 6. And we have a graph here. 1970 represents t equals 0 for us, 1980 t equals 10, and so on up through 2020 is t equals 50 with the populations at those times shown. This is population of Las Vegas metropolitan area, t years after 1970 given in the table and then given in the graph here. So first, let's find the average rate of change from t equals 80 to from 1980 to 1990. So that's from t equals 10 to t equals to 20. So this is the average rate of change. Is 853,000 minus 528,000 over 20 minus 10. 853 minus 528 is 325,000 over 10. And so that's 32,500 people per year. And if we look at the graph here from 1980 to 1990, from t equals 10 to t equals 20, this secant line right here, let's see, is that a good approximation of what goes on at 1985, which is t equals 15? Yes, that seems to match very well. So the slope of the secant line passing through the population curve at t equals 10 and t equals 20 is approximately equal to the slope of the tangent to the curve at t equals 15. That's A. Now let's go ahead and let's look at the average rate of change from 1970 to 1990. So this is t equals 0 to t equals 20. And that's going to be delta P over delta T this is 305,000, and 1990, still that same top number, 853,000. Now this is 20 minus 0. 853 minus 305, 4, that's 8, 4, 5, 48,000 over 20. So 2 goes into 5 2 times with 1 left over. 2 goes into 14 7 times. 2 goes into 8 4 times. 2 goes into 0. 2 goes into 0. That's 27,400. And then if we look at the from 0 to 20, which is this secant line right here, and we look at what goes on with at t equals 20 right here, because we're told to use it to estimate 1990, that's an underestimate. We have a lower slope for our secant line than we do for our tangent lines. So that's not really a good estimate there. All right, that's it for this video. We'll come back next time and talk about 3.1 Objective 4, where we use limit definitions to evaluate derivatives at given points. Basically, we already did that in the last video, but we'll come back and we'll do that again. So see you for the next video.